Welcome back. This is Transistors Part 2. We're going to talk about Darlington Pairs, problems of beta, voltage divider biasing. So a Darlington transistor pair is we take two transistors and piggyback them together to increase their beta. So we have transistor Q1 here, Q2. What we do is we connect their collectors together. Q1 and Q2 collectors are together. And then we take the emitter of Q1 and we put it to the base of Q2. Now, what this appears is this: if it's one transistor, we have one base lead, we still have a collector lead, and we have emitter lead. The total beta is beta 1, the beta of Q1, times the beta of Q2. So if these were two N3904s, it'd be 100 times 100. We'd have a total beta of 10,000. So that's extremely high beta. Here's an example where what we're doing is using a power transistor. Power transistors have very low betas. Their job is to handle high currents. One of the trade-offs is they end up with a low beta. So typically their beta could be anywhere from 5 to 20. 5, 10, 20 is very common. So we have a power transistor with a very low beta of 20, which means it doesn't have a very high current gain. What we could do is piggyback a smaller transistor like a 2N3904, small signal transistor that has a high beta, like beta equals 100. You can do this with two separate transistors, or you can actually get Darlington pair transistors that are already built that way. So if we look at the beta for this one, we end up with the first beta of 100 from our small signal transistor Q1 times the beta of our power transistor of 20. We get a beta total of 2000. So why bother? Well, extremely small base currents can control extremely large collector currents. So as an example, we said we had our beta total of 2000 with our power transistor and our 2N3904, our small signal transistor. What we can do is we can put a small current in, like 5 milliamps in, and that would be the output, let's say a drive from a logic gate. And what we find out is that when we look at our collector current, our collector current is equal to the beta total times the base current. So our beta total is 2000 times 5 milliamps. That will give us 10 amps. So with the output of a logic gate running 5 milliamps, we can control up to 10 amp objects. And they can be large motors, they could be fans, they could be relays, they could be solenoids, it could be any number of things. So with a digital logic circuit, you can easily control large power devices. There are problems with beta. Beta's very first one, it's temperature dependent. So as the temperature changes, beta changes linearly, right? It's changes so much that some designers have used transistors as temperature sensors. Another problem is a wide tolerance. We've been talking about the 2N3904, and we say its typical beta is 100, but the actual spec says the beta could be anywhere from 50 to 300. So that's quite a range. If you're going to design a circuit and you're saying, well, hey, I have such a range, it makes it very difficult to it's easy to make one circuit work, but if you're a manufacturer, it's very hard to make 100 work when you have a high range like that. In the lab, we found out that it ranged typically from 70 to 100, and these are the results that I saw. The other thing is that it changes depending on the collector current. So the problem with beta is that the more current you run through, you end up with a different beta. Less current, different beta. So besides having a wide range, it ends up that it also changes with current. Once the solution we're going to look at is we're going to design without beta. Beta is current dependent, so what we're going to do is design using voltages. The voltages will force the current. So what we'll do is we'll set a voltage, and that's going to override the current, because now we're dealing with voltage. And this is called voltage biasing, and we'll be concentrating on voltage divider biasing used for a linear amplifier. So our goal is down the road, we're going to take this circuit and we're going to make it an amplifier. So let's take a look at voltage divider biasing. Very first thing is that we have a R1 and R2. That's our voltage divider. It's connected to Q1's base. And then we have off of the emitter of Q1, we have an emitter resistor. And then off the collector, we have a collector resistor going back up to our power supply. So very first thing, what we're going to do is figure out what our base voltage is. And the only thing we have to be concerned with is R1 and R2. There is some effect that the base emitter junction and the emitter resistor have on it, but it's so small we can ignore it, right? So the only thing we're interested in is in R1 and R2. It's a voltage divider. Now, the base voltage is the same voltage that has the voltage that be across R2, which is connected with a wire. So if we look at R2, voltage across this way is the same as the voltage across here. So using the voltage divider formula, VR2 is equal to the supply voltage, that's the voltage we start with, times R2 divided by the total resistance R1 and R2. It's basically what it is, it's a ratio, right? So we put in our numbers, we get VR2 is 10 volts times 20K for R2 divided by the total of R1 and R2, which is 120K. And we work that out, we find out that VR2 is 1.67 volts. So the voltage across our base is 1.67 volts. Now that we know our base voltage, we can figure out our emitter voltage. We know that our base voltage is 1.67 volts. We just figured it out. Now the base emitter junction of a transistor acts just like a diode. So it's going to be 0.7 volts drop across here. So we start with 1.67 volts. We lose 0.7 volts. Whatever's left over is going to be our emitter voltage. So 1.67 minus 0.07 volts is equal 0.97 volts. So now we know our base voltage, we know our emitter voltage. We can figure out our emitter current because we know our emitter voltage, 0.97 volts. We know what our emitter resistor is, 3.3K. So using Ohm's law, we just say emitter current is equal to the emitter voltage divided by the emitter resistor. So that works out to 0.29 milliamps. Now the easy part, the collector current. We know that the collector current is roughly equal to the emitter current. Right? So collector current is equal to emitter current. So the collector current is equal to 0.29 milliamps. So now we know the collector current, we can start trying to figure out our collector voltage. Collector voltage is from the collector to ground. We can't figure that out directly, so we have to do it indirectly. We do know that this is a series circuit going this way, so the collector current will be the same current through our collector resistor. We know our collector resistor value, and we know our collector current, so we should be able to figure out the voltage across our collector resistor. If we know that voltage across our collector resistor, we can use Kirchhoff. Kirchhoff's our old buddy and his voltage law. And he says basically if you start with a voltage, any voltage, if we drop a voltage across a collector resistor, then whatever's left over is going to be our collector voltage. So he says start with 10 volts, we're going to lose some here, whatever's left over has got to be our collector voltage. So VRC is, well, Ohm's law, collector current times collector resistance, and we work that out and we end up with 1.38 volts. So we're going to drop across RC 1.38 volts. We can figure out our collector voltage now. We apply our Kirchhoff's voltage law. We start with 10 volts, we drop our 1.38 volts, whatever's left over is going to be our collector voltage. So 10 minus 1.38 gives us 8.62 volts. So measured from our collector to ground, we'll have 8.62 volts. We have one last calculation, and that's called VCE, and that's the collector to emitter voltage. VCE stands for the voltage at the collector with reference to the emitter. Mathematically, what it is VCE is equal to the collector voltage minus the emitter voltage. We know both of those. We know that the collector voltage is 8.62 volts. We figured that out. We know the emitter voltage. We had figured that out as 0.97 volts. So our collector emitter voltage is 7.66 volts. And that's our voltage from our collector to our emitter. So the question is, why is VC equal to 7.66 volts? Shouldn't it be 0.2 volts? We had talked before about using a transistor as a digital switch, and it was either on or off, right? So when it was in saturation, it would be what we call turned on very hard. VCE sat would be equal to 0.2 volts. We were biasing the transistor to act as an analog amplifier. So when it's an analog amplifier, what we want is to have on the collector a voltage swing. We want to put a signal on here like a sine wave. In order to do that, we have to have some voltage that it can go positive and some voltage that can go negative. If it was just 0.2 volts, what would happen is that we couldn't go anywhere because it's stuck at 0.2 volts. Here we're actually going to be able to ride an AC signal on top of this DC voltage. So let's do a review. When we work with a voltage divider biasing, the very first thing what we do is we find VB, and we use a voltage divider formula to find it using R1 and R2. Once we know VB, we can find VE. So VB is 1.67 volts, then we can figure out what VE is. It's just 0.7 volts less. So it's minus the base emitter voltage. Next, what we do is we find the emitter current. We know the emitter voltage. We had figured out was 0.97 volts. Well, we know the emitter resistor. We can find out the emitter current, right? And that's just using Ohm's law, where voltage divided by resistance gives us our current. Once we know our emitter current, we know our collector current, because basically our collector current is equal to our emitter current. We know our emitter current. Now what we can do is find our collector voltage. We use Ohm's law again. Voltage is equal to I times R. And now we can know what our collector voltage is. Our voltage across our collector resistor is. Once we know our voltage across our collector resistor, we can find our collector voltage. It's just our supply voltage minus our collector resistance. So we have 10 volts here. Whatever voltage this is, subtract that. That becomes our collector voltage. Last one, what we do is we find our collector emitter voltage. We know our collector voltage. We had just figured it out. We know our emitter voltage before. The difference between the two, which is collector minus emitter voltage, gives us our collector emitter voltage. That concludes this presentation for today. All right, goodbye.